Welcome back, physicists. We're about to make the transition. I think at the end of this week, we're going to no longer be physicists, and we will jump to being chemists. So I think that's where we're going. What I will likely do is for the things that we skip, whether it's right now or at the end of the year, we'll just make sure that you have, we'll do really, really brief kind of talk on it, or at least be exposed to the ideas before we make the final transition. Lando. What? Nope, just heads up. Any question like that, again, it's going to mean we don't do anything in the lab. So, like, I imagine you get it. Okay, so check it out. We are in 6.3, and in your notes so far, you have 2 ideas in 6.3, I believe. Last thing in your notes, and it might not be written exactly like this, but we have complex circuits, something like that, right?
Yeah.
And I'm going to, pause here. We have 2 different types of circuits, series and parallel. Can somebody give me a concise, which just means in very few words, how would you explain a series circuit to somebody? Okay, Davian says one path that connects everything. Now you're going to hear language change. You might use path, you might use branch. In either situation, I want to think of a single path. Now, branch, path, or loop are kind of the things that we use. So if I'm looking at a series and I want one path, here's a battery. Does it matter what's on here? Doesn't really matter. What's this? An ammeter. Okay, we did not talk about this one. I'm going to throw you a curveball. What do you think this one is? It's a good thought, but I want you to look more careful. A voltmeter, right? Okay, this one, and I like this way to draw them. That's a light bulb. Now, no matter what, if I follow the flow charge through here, I might, depending on which way you want to go, whether it's conventional, from positive to negative, or the reality from negative to positive, you only have one path which you can follow, right? If you start at one side of your power source, the battery in this case, you can only go one way through, and I'll do it here so that people can see it. If I start, for example, on the positive side, and I'm looking at conventional current, if I start here and I want to complete my circuit, which way would you tell me to go?
Positive.
So you can use direction here. We'll just say it's organized nicely. Do I go up or down if I want to get to the other side of the battery? Up. And then what? To the right. Now I go through that, I go down, I go left. That's the only option that I have, right? That is a single path, a single loop, however you want to word it. The language here, when you hear loop, do you think nice square, rectangular looking stuff, or do you think circular stuff? Okay, in reality, does a circuit care if it's circular, weird, or square? No. Check this out, you don't have to draw this one. Is this the same circuit? Is that the same circuit? Yeah, it looks wildly different, right? It does kind of look like the evolution of a fish. Random fun fact, I wouldn't really call it a fact. Turns out my kid, what's his name? Zeke, there it is. Turns out he really likes watching, so I knew what it was just for the record, right? Turns out he likes watching Smash Bros. That's his thing. We have a Switch. He just wants Smash Bros. He wants 2 people. Mario, because he can say Mario. Yeah, doesn't say it like that, but that's pretty good. And he wants Pika. He wants Pikachu because, one, Pikachu's bright and colorful, and he can say it easily. Learned last night. Never knew this. Wasn't a Pokemon kid. Looking at it, Pichu evolved into Pikachu? No idea.
Who's Pichu?
Didn't know that. Yep. So, anyway, there's your fun fact. Okay, Pichu is what Pikachu evolves from. I thought we just went through this. Check it out. What makes it parallel then? All right, that was multiple paths. Okay, instead of path, what might I say? I wouldn't say current. Multiple paths, multiple branch, multiple loops, if you would rather. Now, when I think of parallel circuits, I'm only going to include light bulbs on this one because it's going to be simpler. Now, right now, if I connect this, and I'm just going to do a big circuit, what sort of circuit have I drawn right now? I'll put a light bulb at the end here. That's a series. How can you tell? Yeah, because of the way that it is, right? Okay. Remind me of that later, because it is the way that it is. Okay, if I wanted to make that a parallel circuit, right now I only have one loop, one branch, one path. Tell me when to stop along this path that I could add another path or a node, we could call it, where I fork or I turn, right? Give me a spot to stop where I can make it a parallel circuit.
Right there.
Right there? Okay. So I'm going to call that a node. This is just my fork in the road, right? Where I can turn if I want to. Where should I go from here?
A little down.
Downward. And I'm going to put a light bulb on this as well. We'll do it that symbol. Actually, I'll stay consistent because it's going to bug me if I mix and match between them. It's beautiful. And that means that's another node, right? Where we can branch out. Now, whether I use the term branch, path, or loop, how many paths, branches, or loops do you guys see on that circuit? Two. Which means, as we're looking at this, and this is like as concise a summary as we can get, right? Just trying to make sure all these ideas stick. This is an option for a path. You come down through that one and light it up, right? Alternatively, what could you do? Go up. Do you have to turn here? No, you can keep going straight. Which means, how many paths do we really just highlight? 2 total, right? Because that first one and the second one I drew. Now, there are more relationships between the voltage, the current, and the resistance that exist here. We will summarize that once we get back to Ohm's law stuff. Before we jump in, those ideas, at least parallel versus series circuits, feel okay. Okay, Lando.
This is kind of about tests, but is it true that every single colored Pokemon is it the
I have no idea. Couldn't tell you at all. I know nothing about Pokemon. Okay, so check it out. As we're looking in this, our notes are going to be a little bit different because we did that investigation in class. If we want to jump on, we have series circuits, we have parallel circuits. What I want to focus on is in your lives, how do they work? So our main topic moving forward in 6.3 still, I want us to talk about household circuits. Okay, household circuits. Right off the bat, circuits don't always look as nice as the diagrams that we made, right? Real electric components require places to live. Are there a bunch of wires in here?
Yeah.
You don't see them, right? We don't see them shocking us. We don't even see them outside, which is a really unique thing to hear. Where do we hide them? Outside, they're in the ground, absolutely. If you live in the valley, yesterday, about 2 hours, there were electric crews digging up that box right there and the one over by the post office as well because we lost power. Yeah, so looking at this, first thing I care about, where do conductors get hidden in your house, in your apartment, in this room right now? Where? Ceiling? Anywhere else? Walls. It must be in the walls also because I have outlets in the walls. Are there any classrooms that you guys have noticed where there's outlets on the floor?
Yeah.
Miss Osmond's class has it. Do you know why?
Because her classroom used to be in a computer room.
That's a good thought. You're close. It used to be a home ec room. They used to plug in sewing machines into the floor. Anyway. Yep, it used to be home economics. Home ec. Okay.
Why did they get rid of it? That was really the best class.
Why do we have a kitchen? I thought that was home.
Maybe it's moved around. Anyway, check it out. We hide conductors in our homes. Hide conductors in primarily 2 places, but really we'll say 3. In
That should make a home.
walls, ceilings, and depending, this is more common if you have a 2-building or 2-story place, but maybe the floors also have some electric components or conductors in them. Okay, normally, if I want to have these on, and this is a question on your quiz, in houses, do we use series or parallel circuits typically?
Parallel.
Why on earth would we use parallel?
Because if it's a single, then we can use one light.
Yeah, like you don't want to turn off your light switch in the living room and now your fridge turns off and all your food rots, right? That'd be stupid. Can you guys think of anything where, in your experience, is done in series, where if one thing breaks, the whole thing breaks? Can you guys think of that situation? Say it again. Hallway lights, maybe. Depends on what you mean by that. So they can still be, they could be part of a parallel circuit, just so you know. Minecraft tree, maybe. I don't know. Okay, nowadays they're getting better. If you celebrate Christmas, what do you typically put around the tree? Lights. Have you ever seen string lights where one burns out? What happens to the rest of them?
They all burn out.
It depends. A lot of the time, though, they'll all burn out because that is done in series. So I'm just going to make a follow-up comment here. In our homes, typically, would we expect a series or a parallel circuit?
Parallel.
Typically a circuit, and we're going to say, instead of saying a parallel circuit, we can word this differently. We can say typically a circuit in parallel. Same meaning, whether you say a parallel circuit or a circuit in parallel. Okay. Nope. Yep. Normally in your house, Angel, parallel circuits are what we use. You can say parallel circuit or a circuit in parallel. They're the same meaning. I just want to make sure you're exposed to both. Okay. Second little piece. In the U.S., we power stuff, and pretty much everywhere, we power stuff in our houses by the outlets in the wall. What's the voltage typically going to be in our wall?
100, no, not 100.
Voltage is either, in our country anyway, 120 volts for small components. Or what about big ones? Your dryer, your 300 is a little bit big. 240. 240 volts or 120 volts is what we normally use in this country. Now, as you're looking at this, where on earth, or where in your house rather, and it's hard to see in this school, where does the electricity enter your house or your apartment building? Like, it has to go from the ground here specifically because we bury our wires. It goes through a power box. Typically what color?
Green.
Green are the big ones outside. Residential ones aren't green.
Gray blue.
It's that grayish color. Maybe it's a little blue. I don't see blue, but that's like maybe, right? Okay. So normally it doesn't because you're not supposed to paint them. These things, whether it's parallel or series, which if it's our house, it's parallel, just to be honest. But these things all enter, or all branches. You want to use branches, paths, or loops? All branches, especially in a house, all branches, and I'll write that nicer because I can't read that. All branches start at the same place. Now, when you see this, depending on where you live, sometimes you'll be inside the house, sometimes you'll be outside, or maybe you'll have a little bit of both. But the place that these enter are typically a gray box that you will see in your house or outside of your house.
Doesn't it have like circles on it?
There could be circles. A lot of times you see little black things on it. Little switches, which we're going to look at. So that starting location, it turns out, is a nice way to transition into our next little subtopic. So these are all just kind of comments about household circuits. We're going to dig into a specific part of these circuits, and we're going to talk about these safety features. Now, theoretically, if you're going to be using electricity, you don't want to be electrocuted to death, right? Like, presumably, that's something you want to avoid, or whether it's fatal or not, you really don't want to get electrocuted at all. Who in here has been electrocuted even a little bit? It's not comfortable, right? What's it feel like?
A shock.
It's
like, I don't know, it feels like lightness in my heart.
I can see that. Okay, does it make your muscles tense up or relax?
tense.
Why?
Because it's like shocking.
No, I think it makes it like
It makes you hold on more.
So, like, if you ever see somebody, and there's scenes of it, if somebody grabs a wire and they're electrocuted, can they let go?
No.
Not normally, their muscles tense up. Now, you haven't taken biology. How does my brain tell my hand to close right now?
firing neurons.
Neurons, right? It sends along these specific paths, and you might not know it, but it's essentially an electric charge that flows along that path.
More like
I have circuits, quote unquote, in my body. So if all of a sudden I'm introducing a bunch more electrons and more electric current, maybe it confuses my muscles, my neurons, and they can't function correctly. That's what you're feeling. You're feeling that tense up, odd piece.
They use that for like stem cells, right? With the like therapy for shock therapy.
So, very controversial topic. There are applications that are like for Parkinson's, for example. Parkinson's is a disease that leads to uncontrollable tremors. And if you look at it, like, we don't have to do it, but if somebody has Parkinson's, so in our homes, I care more about this, safety devices than anything. Now, as we start to get more and more devices along a particular path, like think about your kitchen. If you think about your kitchen, I'll tell you, your stove is not going to be on the same circuit or the same path as your fridge. They won't be. However, your fridge, the lights there, a freezer if you have it, the garbage disposal, like all those things are going to be on the same circuit. All your small appliances, your blender, your KitchenAid, like if you try to turn on a big microwave and a mixer at the same time, you might lose power in that room.
I've done that.
Yep,
We have
it
an air
happens.
fryer and our
Yep.
microwave on the same one, and we turn them both on, and the whole thing.
Same thing happens to my house because there's too much energy trying to be used. Yo, try to hustle, okay? Now, if we're looking at this, these safety features, if we have more current flowing because we need more current to power everything, too much current can be dangerous because current can change from electricity to heat, which if you start heating stuff up really high temperature because there's too much current, what's going to happen? It's going to burn. So like, let's say the wire starts on fire, melts the rubber, and there's a little bit of heat coming off of it. What else is at risk? Your house, right? You're going to, like, the whole house could possibly burn down. Now, the good news is there's some things that are common everywhere that we can deal with. So the first of these safety devices that I want to look at is a fuse.
Your fuse box.
So fuses, you do not typically see. Fuse box in a vehicle or a car, you will come across regularly. Those of you that, like, as you guys start driving over the next few years, you will likely encounter fuses in your car. You'll have to at some point. Now, fuses, these are a single-use product. That, and I'm going to put in quotations, a single-use product that melts if current gets too high. This is like a dark red, yeah. Okay, a fuse is a single-use device or product that you hook into a circuit somewhere and it melts if the current gets too high. Now, when we talk about melting, if you've never seen a picture of a fuse, I'll grab one up here. I'll just post it. Now, this fuse, for example, notice I have metal, which means current probably enters one side, flows through here, and then enters out the other. Now, just like an old incandescent light bulb, which are the ones that get hot, they have those little coils on them. What part of this do you think melts? Do you think I want the entire everything to melt down and possibly get too hot? Probably not. Do I want it to be hot enough to melt the glass on this fuse? No, that'd be crazy hot. Notice, though, there is one little tiny wire that runs through it, right? Depending on the size of that wire, it can handle a different amount of electricity, right? Thicker wires can hold more current. This little piece right here is a part that melts. Now, it just pops. It's all happening, just boop, and now it's disconnected. Our circuit is no longer closed, which means what no longer flows through it?
Energy.
Current, energy specific, or energy, but current specifically. Okay, fuses, one-time use. Would it make sense for me to hide a fuse back here in the wall?
No.
Why?
It'd be hard to get.
It'd be hard to get to, right? Now, in your vehicle, if you ever sit in the driver's seat, if you look down to the left from when you're sitting there, there's usually a little box you can pull out, and you'll see a bunch of little fuses. It might be there, it might be in the hood, it just depends. Yep, there's a bunch of fuses, because does your car use electricity?
Oh, yeah.
Like, all over the place, right? There's tons of computers in a modern car. Okay, beyond that, there's a bigger piece. This one, we don't see very often. Fuses, they exist. They definitely get used, but we don't deal with them on a regular basis. What you do see more often than not is inside your house, we talked about that gray box, right? You know what it's called? It's a breaker, specifically a circuit breaker. Because if you have too much energy and it's getting dangerous, you don't want that circuit to run, right? You want to break the circuit. You want to break the path down. Now, circuit breakers are much nicer than our fuses. These are multiple use. So I'm going to actually do it here, just so I can stay consistent. We'll say that a circuit breaker is a box containing a safety switch for every circuit in your home. Okay, circuit breakers, the specific breaker itself, actually a pretty sophisticated piece of technology. We haven't talked about it yet, but turns out electricity and magnetism are related to one another. If you have electricity running through it, you can make what's called an electromagnet. So you can make stuff act more or less magnetic depending on the amount of electricity.
Use a coil, right?
Kind of. You could use a solenoid if you wanted to. Okay, with these circuit breakers, the nice thing about them is multiple use. So multiple use And then the follow-up about it is that circuit breakers open a circuit, which does that mean turns on or off? If it's open? Open would be off, right? This open a circuit or opens a circuit if current is too high. Okay, just a quick check. Who, when I say circuit breaker, when we talk about the gray thing in your house, you still have no idea what I'm talking about. You think of a car with a circuit breaker? So I'll show you exactly what I'm looking at and what I'm thinking of. Here is a picture. You do not have to draw it. Yeah. Okay. Yes, ma'am.
That I have that in my old room. So since I switched my brothers, they keep playing with that thing because it was a.
Make sure your parents know.
Yeah.
Okay. So the way that these work is if you ever have turned on too much stuff and you hear, if you're close to it, you'll hear like an audible, like you'll hear a click. Because what happens is these things are held in place by a particular current and there's magnet in there. Now all of a sudden if the energy gets too high, it means there's not enough energy in each switch to hold that magnet closed still. So if it's not being held closed, what's it going to do?
Pop open.
It's going to literally click and pop open.
Is that
Now,
what you have to
the
do?
good news is that if you pop a circuit, or you might call it blow a circuit, like somebody blew a circuit breaker that didn't really blow it, that would be terrible. Okay, what you have on here is this switch will just straight up flip. Okay, looking at it, a very literal, physical flip the switch. Like you're just going to push it the other direction, it'll close it again. If you ever pop a circuit breaker, you need to turn off the devices that led to it to pop, because if you turn it on and the current's still too high, it's just going to pop itself again. Now, this one you'll notice, and they all have different numbers of stuff. This one is labeled well, which it should be. And if we can zoom in a little bit, and King, are you good? You do not have to draw this picture, just so you know. Okay. If we could zoom in, you can't really tell, but what's written here, do you think?
Numbers and
Yeah, so check it out. I can tell this first one, can't tell anymore. I think it says air and heating. So this one right here is what's going to come, like the powers the furnace and the air conditioner. This one big one. Now notice, this single one right here is bigger than that. Why? Yeah, you need more energy, right? So not necessarily voltage. You are right, it's going to be 240 volt, but you need more amps. Each one of these spots can be popped out, like you could use a screwdriver and pop it out and add another breaker to this circuit box. Okay, what you don't see up above is realistically, if you open this up, inside there is from outside a thick collection of wires, and then what's happening inside is this, where it's going to each one of them. Now, I'm not going to make you draw it because it's really convoluted. There's a lot of different circuits here, but this is a huge safe device, really important. Okay, feeling okay so far? Questions, concerns? Okay, so moving forward, should we get a little mathy? What do you think the correct answer is there? Yeah, obviously we're going to, right? Whether I want to or not, or you want to or not, it's gonna happen. So check it out. We're gonna get mathy here pretty quick. Gosh, you know I completely forgot. Just as a quick reminder, can you Ohm's law? There's a relationship between voltage and current and resistance, right? So my challenge for you right now, before we write anything else, is I want to make sure we have a little recall. I want us to recall Ohm's law. So using your notes, your book, whatever it is, I want you to tell me the relationship that we wrote down between voltage, current, and resistance. There is Ohm's law, and this is fine. What's I represent? Current, and V? Potential difference or the voltage, good. And R? Resistance. Follow-up question. Let's see here. Kyle, if you know, awesome. If you don't, we'll work it out, because I don't remember if you were here when we talked about it. Current, what's the label or the unit they would use for current? Like 15 currents isn't how I'd say. It'd be 15 amps. Awesome. Lando, potential difference, this V, you measure it using, gosh, what's the letter? Volts, V, right? Okay, this last one, R, this is the hardest one by far. Trace, resistance R gets measured in watts. So I is current. So current is in amps. Potential difference is in volts. What is resistance measured in?
R.
That's the letter we use. What's the unit? Ohms. Okay. Ohms. Okay. Right? Ohms. Okay. Now looking at this, I prefer, and I hope that you guys prefer as well, possibly using this little triangle. I think the triangle works nicer, especially if you don't love the mathematics. How does this triangle look? What goes on top? V goes on top here, and then underneath we have I and R. Who knows how this works? Like, can you explain this to me real quick, Angel? If I want to figure out voltage, like if I don't want to have to remember all the variations of this formula, how do I do that? How do I use this triangle to help me with that?
Like you cover one up to see which one you have to find. Like if you want to find voltage, you cover the V,
So I cover voltage, good,
and then I times R.
and then I times R, because they're next to one another, right?
If you want to find resistance, you just cover the R and then
V divided by I, right? I can rearrange automatically. Okay, now we will be using Ohm's law, but we're also going to be using an extension of Ohm's law as well. So, our last main idea here, and we'll see how far we get into it. We may have to push back the test depending, because our dang 4-day week. We'll see how it goes. Our next focus is going to be on two ideas. This is our last main topic of the chapter. We are going to be discussing electrical power. Electrical power. And energy. Okay. As we're looking at it, electrical power and electrical energy, they're obviously both related to what? Electricity in general, right? Maybe you call it electrons, flow of charge, however you want to word it. But it shouldn't be a big leap to say electric power and electric energy both deal with electricity. Now, we do have specific language that we're going to use to refer to these, though, and specific definitions that I want to make sure we have access to. So our first kind of topic in here is let's take a look at electrical power. Now I'm going to make this a vocab, and I'm just going to call this electric power. Okay. When you think of power, there's a lot of different ways you can think about it. Somebody who's powerful, they do what? If a person is powerful.
More control.
More control?
Yeah. Power equals power.
Okay, so there's a whole lot of different ways. Power is really vague, right? Elon Musk, I don't think can deadlift more than most people. Maybe he can, but Kennedy makes a good argument that Elon Musk is considered powerful. Why?
That's
He
because
has a lot of stances.
has more resources and he knows how to use
He has a lot of opinion, like he has the ability to sway opinions possibly, right? Like maybe he does, maybe he doesn't, that's not the point. Okay, he might be able to do it. Okay, what about physical power? Okay, like more powerful, you can lift more stuff, I imagine. Okay, more weight. Okay, when we're talking about electric power, really important, we are referring to a very specific idea. When we talk about electric power, we are talking about the rate. Which, when we talk about a rate, it's the amount of change, how quickly change happens. The rate at which electric energy is converted into other forms of energy. And I say other forms of energy. Now, I don't want us to have to write these down, but I do think there are a couple really easy ways to think about it. First thing is, this varies by the device that you're talking about. The amount of power required to operate a particular device varies wildly as we're looking. So, as we think about this, we're going to see it's measured in a specific way, and there's a way to calculate it. But let's think this out. Do they make electric bicycles?
Yeah.
Okay. Do they make electric automobiles, cars? Okay. Is it possible that I could hook up the same battery to a bike as a car?
No.
So let's pretend that I have like a way to do it. Let's imagine I could use a gigantic car battery for a bicycle.
Oh, that one.
Okay. So you might think so, but remember
But it's gonna burn.
that
Go, you.
amount of energy held in there, the voltage doesn't really matter. It's like I can make it whatever voltage depending on a whole bunch of different factors. But how fast that energy gets changed matters, right? What do you think changes energy faster and has to change faster? The motor that powers a bicycle or the motor that powers a vehicle?
A car.
It has to use more energy, right? It has to convert it faster because why?
There's more.
The car is heavier, right? You have to use more energy at a faster rate to get the car to move, even though the energy is all the same type of energy. Angel.
You know those little car things that little toddlers can
Mhm.
run? My dad changed the battery of that one and replaced it with the drill battery.
It went faster.
Yeah, and it was faster, but it tells them the students didn't have to do it because it will burn.
Yep, it could, definitely. Now, as we're looking at this, electric power, it's the rate at which it's used, which means there's a few things that just really concisely written, we can write nicely. It depends, and it is dependent on the device.
But for some reason, the battery dies so fast.
So remember that it's just the amount of pressure that is pushing the energy through, right? So if more energy gets used over a specific amount of time, things have to go faster to account for that. Now, normally the sort of energy that we're looking at, especially with a car or a bicycle, we are changing electric energy and we are changing it into mechanical energy, something to physically move stuff. Not the only way it can happen. Your microwave doesn't change into physical stuff, Lando. Your microwave changes electric energy through a pretty fancy system into microwaves. So they change into a different type of energy. As we're looking at this, check this out. Depending on the device, an easy way to think about that is your stove or oven requires more power than something. So what does a stove or a oven, if it's electric, require more power than? And there's probably a bunch of these. Give me any device that you use on a daily basis that has electricity. Your phone, what do you think takes more energy to run? More power? Your stove and oven or your phone? Stove and oven requires more power than a phone, guaranteed. Anything else? A what? A fridge. I'll tell you, it requires more than a fridge. I don't know that I agree with your car comment, Lando.
Car because it has a battery in it that, and some cars have batteries on in it, like the electric cars, so they can go.
Not sure I understand the point there, but I agree with
It
you.
depends which car.
It does, but I'll tell you, odds are that your car requires more electric power. Sorry? Yeah, gaming system. I'm just going to say computer. Okay, I'm not going to list all these, however many devices. Okay, we have a phone, a fridge, a light, a microwave, and a computer, and etc. I think that your stove and oven requires more power than any of those. And it does, and we know it does because there's 240 volt that powers that device. Now, one of the things that's naturally going to have to happen then is if we talk about power being used and whatnot, we need a way to calculate it out. So, last little section for today, and then we'll jump into our math piece. If we're talking about electric power, it makes sense we would want to calculate it. So here we go, calculating electric power. Calculating electric power is our focus. And time-wise, just because you guys, I assume, do care, I don't think we're going to be able to take a test Friday, just because we're not going to quite finish today. Well, maybe, yay. I don't know. Is a Monday test better than a Friday test?
No.
Well,
Friday test is better since you have more knowledge about the subject. You're not brain dead.
I mean, it depends, right? If you're going to use your weekend to study, Monday test is better. So check it out. Okay, you're good. Okay. Regardless of Friday or Monday test preference, here we go. Big important idea. We're going to get the wordy version. Remember, we always do the wordy version and the mathy version. So this is our first kind of mathy version, or wordy version. Thanks. Now it's better. Boom. Okay. Here we go. First thing, we're going to say electric power. And I'm going to use, underneath, I'll write the units. Electric power. Bless you. Bless you. Which we measure in watts. Gosh, we had watts already this year, didn't we? When did we use a watt? Energy, what about it? Sorry? Nope, we did it long before electricity. We saw watts elsewhere because I remember going, what? Over and over and over. Yeah, exactly. Okay, electric power measured in watts, it turns out is exactly equal to the current that you are using. Which, how is that current measured?
C.
Amps. I is the label, right? And we'll change that, but it's measured in amps.
Wait, why is I the label if it's amps?
Okay. Times, and this one I'm going to write different than we have been. I'm always going to call this potential difference. Which, the potential difference, I like this language so much more than what your book uses. This is volts. Or your voltage. Because I don't think it makes sense to say the voltage is the difference in voltage. That just feels like it's redundant and doesn't really mean anything. However, you talk about the difference in charge between two regions, potentially, and that makes sense. Okay, electric power, turns out you can get by multiplying two things. What do I need to multiply to get electric power? Current and voltage. I'm cool with voltage if we use it. You don't have to use the word potential difference. Potential difference is the formal version. Now, more specifically, what we're going to do is we're going to represent this using very specific letters. For power, thoughts on what we might use?
P.
Capital W-Y-W. Watts is a good thought. I'll tell you, because we use capital W for the unit, that is how we label watts, we're going to use capital P for power. Okay. So check it out. Power, P, is equal to, what's current? I. Times, what's potential difference? V, or voltage. Now, we do not get to play the super physics game in here, which maybe you're into or maybe you're not. Where physics gets, I think, to be more fun, like a puzzle sort of feel, rather than just saying, here's a formula, use it, which is kind of just plug and chug mathematics. I don't necessarily love that type of math. I don't hate it. But check it out. Is there anywhere in here that these letters show up? Yeah. I, V, and R.
Yeah.
Are they the same I and V as this? Yeah. I think so. Which means there must be a way, like you could substitute and solve back and forth between these equations, right? And you could start to see that maybe I solve one for V and I could plug that into the other one. And it can get complicated or fun, depending on your language. The good news is you're not going to have to do that wildly. Okay, real quickly, we're going to check. P equals IV. That is the formula to calculate what?
Watts.
It's going to give me watts in the end. Power. Okay, real quickly here. Rylino, what does this P represent? Capital P means?
Potential difference.
Not quite. Show me. Where did you get that from?
What I want us to do, we're going to draw your thing real quick.
Okay, we're going to try that one more time. Rylino, what does that P represent? Okay, watts is how we measure what? Power, perfect. I would like Davian to tell me what this I represents. What's I? Current, fantastic. And let's see here. Miss Bice, what does this capital V represent? Volts, give me a different word for voltage. Potential difference. Okay, using a little editing magic for any of the travelers, we're going to do a problem together. So here we go. We'll call an example here, and I'll tell you, we are going to be calculating out electric power, just so you guys are aware. All right, so here is our question. We have a dryer, which I didn't write down. It's a clothes dryer, like you would use at home, that draws or uses 15 amps of current when we plug it into a 240-volt outlet. I want to know what is the power in watts required or used to run this dryer. Now, The good news is that no matter what problem we're doing, whether it's a physics problem or a chemistry problem or whatever, we're always going to write out the same thing. The know, the find, and the equation and steps, right? So, right off the bat, I'm feeling a little blue. I'm not really, but my knowns are here. Now, the one part that people miss, and I feel like I've taken points off of every single test for at least one person. When you're writing the knowns, almost inevitably, somebody in here is going to have just this. You can tell that you've been given 15 amps. That's half the battle, right? This mistake, people always, not everybody does this, but it happens. What mistake did I make when writing that, do you think?
You didn't put the
I need to be able to know what it is, right? Where am I going to plug it in? And this is the important part. Amps tell me that I'm talking about the what? The current. And what label do we use for current? I. A capital I specifically. Lando, give it back. Okay. What else do I know about this problem? Kyle, we didn't make eye contact yet, but we are now. What else do I know about this problem? I know that the current is 15 amps. Anything else?
The potential difference is 240 volts.
Good. Now, I'm always going to refer to it as potential difference. I think this feels dumb when I write it. I'm totally cool if we say V equals 240 volts. Kind of drives me crazy, but are you guys okay with it?
Yeah.
I don't love it, but I don't have a better way to do it. Okay, anything else that we know? I don't think so. What am I supposed to find?
Power.
The power of P, right? So here we go. We're trying to find, and I don't even write power, just P. Is there a relationship between power P, current I, and voltage V?
They are.
What's the relationship? Oh, it's IV, right? Whoa, so here's equation.
So you could say like they're the same. Like,
P equals I times V, right?
those three properties are the same.
What do you mean?
Like current, resistance.
They're not the same, Definitely not the same. What do you mean the same?
Because didn't Ohm's law said that those two were kind of.
They're related.
Yeah.
They are definitely related. But check it out. What's our current? 15 times voltage is 240. And with a calculator, could you guys do this? 3,600 watts. Watts. Okay. Boom. 3,600 watts of power is what it takes. Tomorrow, bring your math hats. We're going to be doing some of this and then finishing the chapter.
We don't have to go through.
We'll try. Adios. No homework tonight, with the exception of anybody who didn't hand in the lab. It's going to be a 0 in the grade book for now.